Okay, so then I will just go ahead and start to the talk. So the title of my talk was Optical Investigations of the European-based iron nictide superconductors. And then initially I decided that I will focus on this 1144 system, which was the newest member. Well, the first two talk actually presented some of the results already, but I hope there are still something to tell about that. Okay, let me see. Somehow the laser pointer doesn't work. Oh no, that's fine. All right. Then let me start with just a brief introduction, as we heard about these systems quite a lot by now. So the parent compound is superconducting with a transition temperature 36 Kelvin, but there is no spin density wave transitions observed like the other iron nictide superconductors, which also when we consider that this system is kind of intertwined 1-2 systems, two intertwined 1-2 systems, and that was also a surprising result. Well, this spin density wave transition actually appears when you start to dot these systems. But what is interesting about it is because of the europium sublattice that orders ferromagnetically below 15 Kelvin, it's actually quite an interesting system. So, well, even though europium actually orders below 15 Kelvin, in the resistivity there was no re-entrant superconductivity, which also reported for some other iron nictide superconductors, for instance, this rhodium dop 1-2 system here, where you basically start to see your superconductivity appears, but in the ordering temperature of europium, it breaks down. Well, this was not the case for this 1144 system, but nonetheless, we just wanted to know what is the effect of europium ordering, as it seems to affect quite a lot in other iron nictide superconductors, and how it actually affects the superconductivity. So obviously there are a lot of experimental methods to tackle this problem, or let's say these questions. But being an optical spectroscopy group, that we wanted to look into these questions by means of Fourier transform infrared spectroscopy. So I put this slide so because it's maybe not so familiar to everybody. So basically, we measure the reflectivity of our samples in a broad frequency range. So this is our frequency range, and this indeed covers a really quite broad range. And I put two energy scales here, so you can choose whichever you want to use. And in the optical spectroscopy community, we always use the inverse centimeter. And our temperature range was from room temperature to 4 Kelvin. That 4 Kelvin is significantly lower than the transition temperature for the system. This is just an additional information that we actually performed the measurements in 3 different setups. For the infrared part, we used 2. That's why we had some empty spots between two different measurement setups, but this is not really significantly important for the discussion of superconductivity and superconducting gap. So once you have this reflectivity that we performed in plane, as iron nictides tend to be quite thin, you can do some Kramer's chronic analysis on it, and then you can obtain the other optical variables like optical conductivity, as I showed here, or the dielectric function as a function of frequency. And once you have this, then you have some model fits, which here one can see a couple of Drude components, some Lorentzians and interband transitions, and one can just decompose the spectra by using these model fits. And also, similar optical studies has already been done before we actually did it in the europium compound. It has been done for the calcium-potassium 1144 system, and it was actually looking like pretty much any other iron nictide systems with 2 Drude components, with high energy transitions. When the system becomes superconducting, then 2 superconducting gap opens. Well, actually, one interesting was that for this re-entrant superconducting material, there was actually some reduction in the superfluid density or the gap size when the europium orders. And this was also one of the motivations that we wanted to do more temperature points below the superconducting transition temperature, and just to see if a similar effect is also observed in the europium case. So now the results are based on the manuscript that is already published a very long time ago, but maybe now it's time to discuss a bit more on the details. So this was just the characterization of our sample, and back at time, it was consistent with other groups. By means that's just there was another publication out there on single crystals, and it was consistent with that group. So we quite nicely see the European ordering and also the resistivity of the sample that used in optical spectra was quite nice. So the RRR ratio was quite high. The transition temperature showed 36 Kelvin transition, and everything seemed to be nice. The samples were quite small though, well, around maybe less than 0.5 millimeter, which is for an optical spectroscopy standards was quite small actually. Therefore, you see a lot of wiggles in the spectrum, which we didn't like too much. But at the end, back at time, there were no like bigger samples available, big and homogeneous samples available, and we could actually discuss quite a lot about the superconductivity with the data at hand. So when you look to the reflectivity, actually the sample is quite metallic. When you look to the high temperature response, the reflectivity increases monotonously towards lower energies, indicating a highly metallic nature of the sample. And when you pass to, which is below the 38 Kelvin here, to the superconducting state, actually the reflectivity shows a step-like increase that almost reach the unity, which when you just convert this reflector to the optical conductivity, then what you see is some sort of Drude-like increase in the low energy range. So at room temperature, maybe it's a bit more clear. And once the system goes into the superconducting state, the conductivity drops to 0. So all the Cooper pairs just condense to the delta function here, and then you could observe this superconducting gap. I just plot here at room temperature and in the superconducting state, the optical conductivity in high energies. Well, there you see a couple of interband transitions that is pretty much temperature independent, and for the discussion of optical conductivity, for the discussion of superconductivity and the European ordering is certainly at this point is not very relevant. Okay, then one can just go ahead and decompose the spectrum into different parts, which we try to follow, of course, the other iron nictide superconductors, which also quite nicely fit here, actually. So basically, you have these two Drude components. One is narrow and the other one is rather broad. And in the iron nictide community, it's always known this is the case when you decompose optical conductivity spectra, so you always come across with broad and narrow Drude components. Then the high energy transitions, interband transitions are there. And for the europium case, which was different than the calcium-potassium case, that there are some low-lying bands, which I showed here with the orange color here. And when we move to the superconducting state, everything pretty much stays the same, except the Drude component that gives you the interband transitions in your system is basically contributes to the superconducting gap, so you can describe it with a Matisse-Bardeen approximation, where then this low energy part of this Drude component just disappears. Well, as I said, these low-lying features were kind of weird and is different from the calcium-potassium case. So here I plotted the intensity of these as a function of temperature and frequency. Well, the origin is actually not clear, and it's also not clear at the moment, but they kind of respond to the superconducting state. So when we go into the superconducting state, they kind of split. And in the europium ordering, temperature is basically some sort of a redistribution is there. So the intensity in the low energies increased a bit more, in the high energies it decreased a bit more. At that time, we had a suspicion that maybe there are some europium bands, not necessarily F bands, but europium band sits very close to the Fermi energy, and then when the Fermi energies start to gap with the superconducting transition, And we start to see these double transitions between these bands and so on. And of course, when the europium orders, they also feel a bit, but this actually never been proved, because technically when people look for the dominant bands around the Fermi energy, they of course look for the iron bands, which is indeed the dominant one. So it would be nice to know if there is some europium bands around the Fermi energy. Okay, so even though this low-lying features was weird, but this clearly shows you that it's actually not coming from the system or not coming from the setup, the measurement setup itself. It's something intrinsic to the europium system, which is missing in the calcium case. Then we move to the superconducting gap, and we wanted to know what is the gap value, of course. Then we start decomposing our 4 Kelvin spectrum with this Matisse-Bardeen approximation. And what we realize is actually the broad Drude dominates the gap feature. So we could reliably get a gap value somewhere around 5 millielectronvolt. And in optical spectra, we always see the transition across the Fermi energy. That's why basically what we see is a 2 delta. But when you convert it then with this BCS constant, it shows you that it's actually in the weak coupling regime. And we couldn't see any clear gap from the narrow Drude component. And this was kind of question mark, because now we have a gap at a weak coupling regime. There's a multi-band system. Then there should be another gap that is in the strong coupling regime, but we don't see it. I will come to that point in maybe next slide. But, well, okay, we could only observe one gap at that time. We plotted the temperature dependence of the gap value and then the temperature dependence of the superfluid density that you can directly convert from the missing area, basically, in your spectrum. And one interesting point is that the gap actually in optical spectra opens rather sharply. This happens quite a lot in iron nictide superconductors, and that the gap opens like suddenly in optical spectra, but not necessarily is the case in, for instance, RPS. So this point is a question mark, so maybe it requires some more theoretical input why it always seemed to open that sharply in the optical spectrum. Then when we look to our superfluid density, we realize that it actually doesn't follow this really isotropic S-wave BCS type feature, but rather the BCS constant is a bit small. And also there is some small dip in the europium ordering, which also tells you that the system somehow feels the europium ordering, but the superconducting features kind of survive even at temperatures below the europium ordering. Okay, so the second superconducting gap, we were curious about that, and indeed the recent RPS measurements reveal multiple superconducting gaps, and we kind of catch this one here very nicely. This one is our like out of our measurement range anyways, but you see that there is a second gap over here around 9 millielectronvolt, which would put you in a strong coupling limit, basically. But we didn't observe it, and when we look carefully at the scattering rate of the narrow Drude, which I plot here for both, but the black curve belongs to the narrow Drude component, it's actually quite small compared to the gap value, which means that this superconducting gap, the larger one, might be in the clean limit, and it would not be then visible to the optical spectra. So if your Drude component is quite sharp, this puts these carriers to the clean limit, which then disappears from the optical spectra as a gap. Okay, so then when we look to our overall results about the effect of the europium ordering, the system certainly feels the europium ordering, but the superconductivity weakens at the ordering temperature, but recovers at low temperatures. So we had several indications for that, like the magnetic susceptibility, where the europium orders, but then the volume fraction recovers, and the superfluid density kind of weakens a bit, but then recovers. Well, the overall system really feels it. All these redistributions happens. I was hoping that the previous speaker would be there and talk about the MFM data quite a bit more in detail, but unfortunately he was not here. But when you look also the system in MFM, in the ordering temperature, your vortex density kind of feels it, but it managed to recover to the higher temperatures. So with that, let me summarize the optical spectroscopy on the European 1144 system. So we managed to actually observe the superconductivity on that systems, and the optical spectra sees only one superconducting gap at 5 millielectron volt, and we suspect that the second gap is in the clean limit. I think this is also one point still looks for some confirmation. And then the system really feels the ferromagnetic ordering, but it's not very detrimental to the superconductivity. And there is some low-lying absorptions, probably due to the europium bands that close to the Fermi energy. That would be also nice to kind of confirm at some point. With this, I would like to thank the people who actually contributed the work a lot. It was kind of a bit crowded group, but I would like to point out some people in person. So the optical measurements have been performed by Andrea in the group of Martin Dressa and First Physics Institute, and our samples were provided by the Chinese collaborators. And these MFM measurements were actually performed by Vasily and Dmitry mostly, and analysis has been done by them as well. And with this, I would like to thank you all for listening this talk.
Thank you, Ece, for
May I ask a question? On page 12, you showed the optical reflectivity versus temperature, and you interpret this flattening marked with the red arrow. You said that it is that this superconductivity weakens at this temperature, and this might be effect of the TM. But in fact, there could be a different interpretation, since you know the values of the 2 or 3 gaps in this material. You could feed the data with using the multi-band model. Did you try this?
Okay, so you're absolutely right. First of all, when we actually did this work, the RPS measurements haven't been done yet, so we didn't know the superconducting gap values for this sample at all. So this optical spectra was the first one who gives some sort of a gap value. We tried to fit this with 2 models, 2 S-wave gaps. It is possible, but technically then the other gap is even smaller than, well, it is smaller than 5 millielectron volt. It is possible, but that shouldn't be really that visible in the optical spectra, because this is out of our range. I mean, I should be able to see what is already observed and plus something larger.